What's up? In this video I'm covering this paper called Chip Placement with Deep Reinforcement Learning. Yesterday I saw this tweet from Anna Goldie where they've just published the Nature version of this work, and I thought covering it because it's a really interesting piece of work. It combines both like the electronics, which is something I have some background in, as well as machine learning, more concretely like reinforcement learning and GraphML. So it's exciting combination and super impactful work, so I thought covering it. And basically what they achieved is they managed to train an RL agent combined with some GraphML for learning nice representations in order to do displacement much faster than what previously was necessary. So they needed, humans usually need multiple weeks to do this, and now it's less than 6 hours, and it's achieving even superhuman performance looking just at the metrics the area. So basically, yeah, we want to minimize the area because we can cram more transistors inside of it and more compute thus. And also they want to minimize other things like power consumption as well, and under certain constraints like density, congestion, you don't want to have too many wires overlapping on a single, on a certain piece of, on a certain surface of the chip. So that's a high level overview. Now let's dig into the paper and see what they did. So in this work we present a learning based approach to chip placement, one of the most complex and time-consuming stages of the chip design process. Unlike prior methods, our approach has the ability to learn from past experience and improve over time. So yeah, that's the main thing. Basically, obviously, prior to this work, there were many other approaches, mainly some optimization-based approaches like simulated annealing and some more heuristics, and a bunch of different theory was developed, but none of those were actually deep learning algorithms. And they say here, our objective is to minimize the PPA, so as I mentioned, so the power consumption, the performance, whereas they mean basically timing. And we'll see what that exactly is. You basically want to make sure that certain logic gates in your flip-flops in your circuit get certain signals on time. So there's these timing constraints you have to obey, and we'll see more details a bit later. And obviously the area, again, more transistors you can cram into the chip, the more compute you get, and that's better. So, and we show that in under 6 hours, our method can generate placements that are superhuman or comparable on modern accelerator netlists, where netlist is just a fancy way of saying a graph that basically tells you how each of the components on the chip are connected together. So whereas existing baselines require human experts in the loop and take several weeks. So that's the main point they're driving here. They automate this, they make it even superhuman, and they make it faster, which is huge. And so why do we care about this? Basically, well, they say it here, the world is moving towards specialized hardware to meet AI's exponentially growing demand for compute. However, today's chip take years to design, leaving us with the speculative task of optimizing them for the machine learning models of 2 to 5 years from now. And the logic is pretty simple. If you can cut down the time you need to loop over different designs, you can experiment much faster. And it's the same thing as in deep learning, where you want to make sure that your training length is shorter, obviously. The same thing that happened with ImageNet training, for example. There we needed multiple weeks, and then finally there was a paper a couple of years ago where they've trained ImageNet a vision model classifier in half an hour or something. It's probably even better today. So basically, when you short those, you can iterate much faster, obviously, and that's really precious. So one nice example of these custom chips is maybe Tesla. That's the first thing that popped onto my mind. They have a customly designed computer vision chip set on their vehicles, and it's not just computer vision. They're also using different sensors, not just the RGB cameras. They're also using radars, etc. So the only thing they're not using, and that's LiDAR, because Elon Musk, as you probably know, rants about those all the time and says that we only need to use RGB cameras. But that's a topic for another video. Okay, so the objective is to place a netlist graph of macros. For example, static RAM, which is basically, you probably know of DRAM, that's dynamic random access memory. These are SRAMs are usually non-volatile, so they are even more expensive, and they are more performant than DRAMs. but they do take more area, so that's a trade-off. Standard cells, logic gates such as NANDs, NORs, and XORs. You probably heard of XOR if you did anything related to cryptography. Onto a chip canvas such that power, performance, and area are optimized while adhering to constraints on placement density and routing congestion. Yeah, for the time being, like, you can just have an intuitive understanding of these, and I guess you already have. Like, basically, you don't want to have multiple wires, too many wires going over a certain cross section of or certain grid cell on your canvas. Okay, that's the high level overview. Now let's dig into the architecture. Let me show you the high level pipeline, how this looks like. So basically, what they do is the following. So they treat this, they pose this as a reinforcement learning problem. And as you can see here, the state is modeled like you have this chip canvas. So currently you don't have anything on it. And basically, as already mentioned, you can treat your chip as a hypergraph. And that means the following. So let's assume I'll just draw macros as these squares. So we'll have a couple of macros, and macros can be, as you saw, like SRAM, or it can be memory controller or whatever. So these are somehow connected like this. And then you have these standard cells. I'll just denote them as circles. And basically, so it's a hypergraph. So that means basically that a single edge can connect to multiple nodes. That's the definition of the hypergraph. And now, so imagine you have a bunch of these. You have hundreds of macros. You have millions of standard cells, and you want to somehow place them onto this fixed size chip canvas. Okay, and so what you do is you somehow, and we'll see the details a bit later, using this graph neural network, you kind of embed this information about the connectivity, and that will be your state. And then you're doing the following. So the agent takes that state and outputs an action. And an action is just take a macro. So we'll be just focusing on placing these macros. As we'll soon see, these will be handled by some forced direct method, which is some heuristic that was previously devised. So yeah, they're just kind of piggybacking on certain other methods to do that part. So they place the macro here, and after that, you get a new state, and then you just output a new action where you place another macro onto the chip canvas, and you do so until you've placed all of the macros, as you can see here. And then from that point on, you use this force-directed method to place the standard cells. So you will just take those clusters of standard cells and will place them somehow onto your chip canvas. And finally, you get the reward. And as you can see immediately, the problem is pretty hard because you get 0 rewards all the way down, and only at the end do you receive the actual reward. So it means the credit assignment problem is going to be pretty tough. I mean, the horizon is not that big. They won't have more than, let's say, 1,000 macros. But still, it's a tough problem. And this reward, as you can see, let me just decrypt this for you. So this is a half perimeter wire length. We'll see what that exactly is, but it's roughly, it kind of takes into account the length of wires you have in your chip, and that kind of correlates positively with power consumption and with area, and we'll see those a bit later. Okay, so that's a high level overview. And I mentioned it here. So our true reward is the output of a commercial electronic design automation tool, including wire length, routing congestion, density, power timing, and area. However, RL policies require hundreds of thousands of examples to learn effectively, as you already know, and so it is critical that the reward function be fast to evaluate, ideally running in a few milliseconds. So in order to be effective, these approximate reward functions must also be positively correlated with the true reward. So the whole point is they can evaluate the real reward, the true reward, but that's super slow, so you have to use these EDA tools. And so they decided to just take something as a proxy, which is fast to compute, A, and B, positively correlates with the things they care about. And we mentioned those already, so that's the PPA stuff. Okay. So while we treat congestion as a soft constraint, so lower congestion improves the reward function, we treat density as a hard constraint, masking out actions, grid cells to place nodes onto, whose density exceeds the target density. So in order to understand this part, we should go and see how the policy network looks like. Let me scroll down here. I'll skip some stuff and then I'll later return. Okay, so this is how the model looks like end to end. Basically, we have two portions here. The first part is the the representation learning part. So we have something called edge graph neural network, some graph neural network they devised specifically for this work. And then we have your basic value net and basically policy network. So this is your actor-critic RL agent. They're using PPO, that's proximal policy optimization algorithm published by OpenAI a couple of years ago. So that part is pretty standard. Now let's see, this part is pretty interesting and novel. So let's see how they managed to parse the net list, so the hypergraph of your components into some representation that contains valuable information that can be used to figure out where to place the next components. So the way they train this whole pipeline is using supervised learning, and the whole goal is to learn how to predict the reward. So that's how they train this part. So they take this part in isolation and they train it the following way. So again, you have this hypergraph, so you have macros, you have some like standard cells, they're somehow connected. It's not that important, okay, like this. And what they do, as you can see here, so if you're familiar with GraphML, if you're not, I made a whole playlist and I'll link it somewhere here. You should check it out, but like I'll try to explain it on a high level. And basically it's pretty simple. So every single node in your graph has a feature vector associated with it. So, whoops, let me delete that. Okay, so you have a feature vector like this, you have a feature vector here. Every single node will have a feature vector associated with it. The second thing is, in this paper, actually even the edges have feature vectors associated with them. So you have something like this. So every edge and every node has a feature vector. So what I do is, as you can see here, so the graph neural network takes in the connectivity information and all of those feature vectors, and it somehow processes these. So what we'll see the exact equations here a bit later, but like basically you just somehow combine those, you manipulate them using fully connected neural networks, you aggregate the neighbors. So for example, this one will somehow take all of its neighbors. So this is the neighbor and this is the neighbor. So it will take those feature vectors like this one and this one, and it will somehow combine them with this one. So it's using this relational inductive bias of connectivity, and it's accumulating those feature vectors to create a new novel representation. So this is going to be something maybe of a smaller dimension. Let's call it V prime. If this was vector V, this is V prime. And they are going to output that as the output of GNN. So as you can see here, edge embeddings. So that's a set. That's a matrix that's of dimension E times basically D sub E. So E is the number of edges in your graph, and D sub E is just the like feature vector dimension. So once you have that matrix, what they do, as you can see here, they do this reduce mean operation. So they just take a mean over, like element-wise mean over all of these feature vectors, and they get a single feature vector that's the graph embedding, okay? That somehow roughly captures the dynamics, the information about this graph. And the second thing they do is they take the current macro ID, so that's the current macro you want to place onto the chip canvas, and so again here you have a table that's n times d sub v. So n is the number of nodes, d sub v is the dimension of your node feature vector, and they just take a single one, so they just take a dv vector here, okay? And extract it. And finally, they have some metadata information like the length of the wire on your chip, etc. So they have some metadata information, and they concatenate all of those. They feed it through the fully connected layer, and that's it. So now, as I already told you, they're going to train this thing to kind of understand, to predict the reward of the placement. And I'll get into details a bit later, but that's it in a nutshell. So once you train that, you use the representations it learned to basically as a Kickstarter for these policy and value networks, and they are trained, as I said, using PPO. So that's it, and now I'm gonna slowly start digging into the details, and later we'll see the experiments and the results they got. Okay. Before I do that, I think it will be quite useful for you to maybe understand a little bit about some electronics 101, and you'll hopefully have an epiphany moment. Okay, so as software, the same thing goes with hardware. Basically, you have a bunch of abstraction layers. So in software, we have, like on the lowest layer, you have firmware, you have something like called hardware abstraction layer, you have drivers, and you have operating systems, then you have compilers, and you have all of those systems that translate the higher level languages into like something that your computer can parse and understand. And finally, you have the application layer. So obviously a bunch of abstractions. And the same thing goes for hardware. So you have on a really high level, you have a CPU, and you have maybe like the direct memory controller. So that's just a device that to whom CPU can just delegate basically certain memory intensive operations. And then you have memory. Like you have a memory block here, and let's say both are connected to memory. Both the CPU and DM are connected to memory. So if you zoom in into any of these components, like take maybe a direct memory controller, you'll end up with two types of circuits. So basically you have combination logic, and you have these circuits which are called sequential logic, which contain the memory in the system. So they are stateful. So if you take a look at this one, so what's the main difference? The main difference is the following. If you have this circuit, this is called inverter. Basically, if you feed it 0, it will output 1. And if you feed it 1, it will output the logic value of 0. And the thing is, with these combination logic gates is that as soon as you change the input, so if you go from 0 to 1, the output will go from 1 to 0 really quick, like maybe in 20 picoseconds or something. Now the trick with these flip-flops, with these memory circuits is, so this is a D flip-flop, it's one of the simplest flip-flops out there. So basically what happens here, you can change this as much as you want, like from 0 to 1, nothing will change here. It's gonna keep 1 here until you have the clock, so the uptick of the clock or the downtick of the clock. And basically, so hopefully you know what like a clock signal is. It's something that drives your computer. It's a basically digital signal that goes from 0 to 1 with a certain frequency, and on each of these upticks or downticks, something is going to happen. So on each tick, the sequential logic gates, so these gates like flip-flops, will change their state. So if you keep 1 here, and then the uptick comes, at that point the 1 will propagate here. And if you change it now to 0, and the downtick comes, for example, then this will go to 0. So these are keeping, they have the memory. That's the main trick. So having said that, let me go even deeper. So let's take one specific gate like NAND. And what NAND does is the following. Yeah, you've seen these if you've ever done any programming, so you know about the AND operator. This is how you write it down in Python. And basically, this is the opposite of an AND gate. So it's just a not AND. And basically, as you can see here, looking at the table, you know that AND gates give you 1 only when you have 1 and 1 as the input, and all of the other values will be 0. And NAND is just the opposite of that. As you can see, it's inverted AND gate. And now this is the abstracted view of this gate. And if you dig a bit deeper and take a certain implementation, which is called CMOS implementation of the NAND gate, which is basically complementary metal oxide semiconductor, doesn't matter. But basically, there are different ways you can implement these abstract logic gates. The same thing as you can do with, if you have a image classifier, you can implement it using a neural network, using SVM, using, I don't know, even k-nearest neighbors, whatever your favorite classifier is. The same thing goes here. You have a bunch of different ways how you can implement the very same thing, and that is the NAND gate. So here we have a specific logic. You can use TTL. There are many different logics you can implement. Now, let me show you why this works. So basically, let's take as an input 1 and 1. And when I say 1, you again have to implement 1 somehow on your system. So let's say, for example, that we have a voltage supply that's maybe, I don't know, like 0.9 volts. And so on this system, 1 will be defined as something close to 0.9 volts, and 0 will be defined as something close to 0 volts. So that's how you implement 0, and that's how you implement 1. And so if I feed 1s here, for example, and so that's 0.9 volts, and if you feed 1 here as well, and as you can see, this small circle again, that means it's inverted. So we'll be adding 0 onto this gate and 0 onto this gate. And what happens is, because you brought a huge voltage here, you're gonna toggle on this transistor, and so the current will start to flow here and here, and you're gonna block these two because you brought 0 voltage here. And so as you can see, you're basically making a direct connection to the output to this thing here. And let's say this is ground, so it's 0 volts, and basically that means your output is 0 volts, which is 0. And let's see, so 1 1, you get 0. The same thing goes for 0 0. So if you bring 0 0, you're going to basically turn off these two, and you're going to turn on these two, and so you're basically bringing the voltage supply directly to the output, which is 0.9 volts, which basically translates into logic 1. And yeah, so that's how it works. That's how your computers basically work. And going even deeper, like people have to design these, and you can see here, so this is how you basically place these metal wires, and this is how you implement an AND gate. And finally you have the last step, and that's the production. You actually do some like photolithography using like light waves. You engrave these into silicon, and this is how a NAND gate, multiple NAND gates look like actually manufactured. And yeah, I had some prior experience myself. I was studying electronics and computer science, and so this was one of the radio frequency circuits I designed, which just takes your signal, like maybe your audio, and basically modulates it so that it's on a higher frequency, and then you can send it over the wire like a radio signal. And yeah, so that was the basically 101 of how computers work. You have these logic gates, you have these sequential gates, and everything is made out of them. So now you know how those macros are all built. And hopefully, like, if you found this useful, please comment down so that I know for future videos whether this is interesting or not. Okay, let's see some of the simplifications they are making to make this thing work and make it like computationally tractable, because the problem is huge, as you can imagine, because of the like millions of standard cells and and hundreds of macros. So first things first, they group millions of standard cells into a few thousand clusters using this tool HMATIS. So that way they basically make it easier for those force direct methods to do the placement like themselves. Okay. And second thing they do, they discretize the grid, so the chip canvas, to a few thousand grid cells. Okay, so that means they won't have, obviously, so you have your chip, and it would be super hard and probably wouldn't be any like meaningful to just make it continuous or to make it really like small resolution. So what they do is they kind of divide these into I think it was 128 by 128 cells. So they have something like this, and they can only place macros on a specific grid cell. So that's the second simplification they make. The third one is, when calculating wire length, we make the simplifying assumption that the wires start from the standard cell, blah, blah, blah. That's not that important. And finally, to calculate the routing congestion cost, we only consider the average congestion of the top 10% most congested grid cells. So again, certain heuristic, which makes it a bit more feasible to calculate this congestion, which is used later on in the reward function. So this part, the half perimeter wire length, is something they use as a proxy, as I mentioned, for training the RL agent, and it positively correlates, as they show, with area and other metrics of interest. So let me just explain to you briefly how it works. And the formula is pretty simple, as you can see. So imagine you have a wire like this, and this is your wire, and basically what they do is for this particular wire, this number would be equal to this thing here, plus, so that's called the height, and this would be width. So that's the half perimeter, right? So the perimeter would be 2 times that. And you can see here, so max over the basically x-axis and minus min over the x-axis, same thing for the y-axis. And if you had something a bit more complex, some wire that goes like this, maybe like this, and finally ends up like this, they'd again do the following. So they would find the max x value, so for this particular wire, so that would be maybe this, and they'd subtract this thing, and they would do the same thing for y. So it's a kind of you find the bounding box, and you find the half parameter of that bounding box. That's it. And then they just kind of combine all of those across different wires. Okay, that's that part. Okay, so certain heuristic, additional heuristic, and you can immediately see, because and I forgot to mention that this work was actually used to design the newest TPUs in Google. So that's the version 5, if I'm not wrong. And so you can immediately see this is in production already. So there are lots of details, but like the high level picture, you already got it pretty much, hopefully. And yeah, let's see some additional details. So to select the order in which the macros are placed, we sort macros by descending size and break ties using topological sort. So that's additional heuristic they use in order to make the action space smaller and to make this problem computationally tractable. So they just sort the macros, so those blocks in your chip by size, and then the policy will just take the next one and then learn how. It just needs to decide where to place it. It doesn't need to learn which one to pick in each step, okay? So I forgot to mention one detail here. Hopefully you already understood it, but like if you have this policy and the output is 128 by 128, so those are the grid cells I mentioned previously, and so it just outputs a distribution across all of the grid cells and where the distribution is, where the probability is highest. So we just take argmax, that's where you're going to place the macro, okay? So it would be really simple if but like additionally you need to mask certain areas. And so, for example, if you have your chip canvas and you've already placed the chip, the macro here, so let's say that's this part, and let's say that's this part, then what will happen is they'll have this density, this mask, which will be used to kind of mask out certain, let's call them pixels, basically to 0. So, for example, if now if the network, if the policy network outputs, I don't know, maybe 0.02 here, and we already have that part occupied, this mask will just zero it out to 0, and you'll just distribute the probability across the other valid cells. So that's that part. And yeah, that's what I mentioned here. So basically, to meet this constraint, during each RL step, we calculate the current density mask, a binary m times n matrix that represents grid cells onto which we can place the center of the current node without violating the density threshold criteria. Before choosing an action from the policy network output, we first take the dot product of the mask and the policy network output, and then take the argmax over feasible locations. So that's the process I just explained. So we also enable blockage-aware placement, such as clock straps, by setting the density function of the blocked areas to 1. So blockage just means that basically you explicitly say, hey, I don't want to have anything placed around this macro, for example, or around this wire. And you explicitly encode that into that mask, and then you can't place macros on top of that location, okay? That's just minor detail. Finally, the loss function. Here is the wire length. I already explained the half parameter wire length calculation. They have the congestion and the density constraint, and they'll just include this density part while Lagrangian, so you'll just have a weighted sum of congestion, density, and wire length. So as for the loss, they are just summing over all of the netlists in the dataset, and they just want to maximize the expected cumulative reward. That was the reward part. Let's now jump into explaining the graph neural network. So our intuition was that a policy network architecture capable of transferring placement optimization across chips should be able to encode the state associated with a new unseen chip into a meaningful signal at inference time. We therefore propose training a neural network architecture capable of predicting reward on new netlists, with the ultimate goal of using this architecture as the encoder layer of our policy network. So that was the part I explained here, the encoder part. And now they say here, we therefore created a dataset of 10,000 chip placements where the input is a state associated with a given placement and the label is a reward for that placement. So basically they used, for example, like those EDA tools, and they found the ground truth rewards. And so they basically had a simple supervised regression task of with this graph neural network called the edge graph neural network. For the computation itself, it's fairly simple. So let's say you have two components here. You have a macro here, and it's connected to this macro here. You have a feature vector here, and you have a feature vector here as well as here, okay? So what they do is they kind of, so they process using a neural network, like a simple fully connected layer. They process these vectors, and then they just concatenate those, and they place it again. They just feed it through another fully connected layer. I'm not quite sure what this part means here, because like it doesn't make any sense to concatenate the learnable weights with the output here. But yeah, basically, yeah, you somehow combine them, and then what you do to calculate the node feature is, for example, if you had multiple edges going into this node, you just take all of those edge features. So you take this edge, you'll take this edge, and you just aggregate those and do a mean across those feature vectors. So the computation is pretty simple. Again, check out my graph ML videos. This will be pretty self-explanatory. Okay, this is just your PPO objective function, and I won't go into details there. Let's see the final results. So on the x-axis, we have different TPU blocks. So they have block 1 through 4, and this open source RISC-V CPU chip. And you can see here the placement cost. So you want to have as low of a cost as possible. So using zero shot basically it means that they don't fine-tune that. So basically what they do is they take the whole system you saw with the policy network, value network, and graph neural network, and they train it on maybe, for example, 20 different chips. And now they take that network and just apply it onto a new chip, like this TPU block 1. And if they don't fine tune it on the block itself, it's just zero shot. So as you can see, zero shot is pretty decent. And then if you fine tune it for 2 hours, you get even better performance. In 12 hours, you get even better performance. But the point is, if they train it from scratch, so without that previous information from those other 20 chips, so it takes, after 24 hours, it still sucks pretty much. It's still much worse than compared to this one that's fine tuned for 12 hours. So this means it generalizes to new, never before seen chips. So that's the benefit of a learning system. Okay. Here, what they show is, again, training from scratch versus fine-tuning. As you can see, basically only after a couple of hours, the pre-trained one gets to really low loss, whereas you need much more time to train. I mean, this is pretty obvious. Bottom line, you want to pre-train these RL agents and then later just fine-tune them onto the new chip you're trying to place. Okay, that's the whole point there. Here they compare, so I mentioned data sets, so I mentioned the largest one, the one that has 20 blocks, but they also trained them on the medium one, which is a subset of this one, and they also trained it on the small one, which is a subset of the medium one. So again, you can see that going to more data gives you like lower placement costs, and looking at this curve here, they are basically, what you see here is the RL cost on an unseen chip, and you can see that with the big data set, you get to overfitting much slower, and you get better performance than basically using medium or smaller data sets. So it's both harder to overfit, and you get lower costs. So again, more data, nothing new there, but yeah. These are the placements they get. So here you can see these purplish blocks are macros, and here in the middle, this like a blob of nothingness is a bunch of basically those standard cells. And here is the zero shot placement, and here is after you fine tune them, you can see there is much less congestion. You can see, so basically these red and orange colors denote that there is a huge overlap across those layers, and here it's much better placed, and you can also see much more regular structure here compared to the zero shot one. But this is still fairly good for something that's working on a chip never before seen. Here are some other results. So here they blurred this because of the confidentiality, but again, you can see the main thing is that humans, when humans design chips, you can see there is a lot of structure. You can see some regular shapes here, whereas this RL agent just outputs this blob and this donut shaped thing here. It outperforms the human design on many different metrics, and that's cool. And they mentioned here like the wire length and the congestion, and you can see that it's both, everything is lower using this RL agent approach. Okay, last table, and I think we're done here. is this one. So they compare it with this replace method from 2019. It's one of the state-of-the-art placement methods, and again, looking at different metrics like timing, area, power, wire length, congestion. It outperforms replace, which not only has lower performance, it also higher cost. It also many times just creates invalid placements because there was too many. The congestion was too big, or there was some invalid placement was made, and so it's harder to get it to work. As a summary, they mentioned here, so for example, the process of standard cell partitioning, row and column selection, as well as selecting the order in which the macros are placed, all can be further optimized. In addition, we would also benefit from a more optimized approach to standard cell placement. So what I say here is potential future work. The first things first is that the heuristic I just mentioned was that they are using the biggest macro first and then the smaller one, blah, blah, blah. So they argue that basically that process can also be learned, and they can squeeze out more performance by doing that. The second thing is, instead of using those force-directed method, that can also be kind of thrown into the RL framework approach. And yeah, that's pretty much it. So great results, super impactful work. So AI is building chips which make AI more powerful. So we have a pretty nice loop here, and it will be exciting to see what else is there to come. So if you found this video useful, subscribe, share it out, and until next time, bye bye.